Excusez-moi. Est-ce que la salle de classe, vous m'entendez ou pas? Il semblerait qu'il n'y ait pas de son sur Zoom.
C'est meilleur comme ça. Okay.
Oui, c'est bon. Merci beaucoup.
Again, criteria for this to be pseudo-effective, criteria for this to be numerically effective, and then the main positivity results. So this would be criteria for.
You might have to go to your bathroom.
Lambda F to be big. And then 2 criteria for lambda F to be ample. And so to actually spell out again what's happening in the statements of those theorems, that takes a lot more to write down. So that's not my intent to do today. But what I do want to do is sort of explain. So there's several steps in the proof. And the proof. And so today I want to discuss sort of outline one step. Outline one step and indicate.
Do you have to go to the bathroom?
An analogous result. Okay, and so here, this is where the Harder-Narasimhan theory arises. Okay, so
what happened to the blue blanket?
what is the question? So recall about Harder-Narasimhan theory here. In dimension 1.
So, can you guys still hear? Can you hear us? In the
Yes.
Okay.
Thank you.
Okay, so I want to recall a little bit about Harder-Narasimhan theory in dimension 1. So see, not maybe clear about how far I should go back, but maybe recall
so I'm a little confused.
Yeah.
And the FD is line bundle.
So in the statement of these theorems, right? So think of the base. You should think of the base as actually being a curve, and so I have to spell out what are my actual assumptions on the family. But you want to sort of think that you have like a family of Fano varieties with polarization given by exactly this line bundle restricted on the fiber. And so the idea is how to prove how is positivity of this basically of the family reduced in that. And so there's, as I said, several steps involved in the proof of this result. And what I want to focus on today is the special, sort of the most important, well, in some sense it's not, but anyways, a very important part of the step of the proof that uses the Harder-Narasimhan theory, and it's interesting for several reasons. And so I want to sort of outline what's the.
You want to get into
Well, because the proof is really
without discussing the statement. The statement.
Well, yeah, so now I'm regretting not like stating the full formulation of the theorem, because it would take several boards to just write down what are the actual assumptions involved, but trying to give some motivation.
I imagine this lambda FT is different from your line bundle curve.
No, so this is the Chow-Mumford line bundle.
It's on a moduli space, not on a curve.
Okay, so what do we mean? So this has to, what does it mean? So yes, so the idea is that the Chow-Mumford line bundle is giving you a line bundle on the moduli space. But I mean, so we haven't, I haven't made the moduli space and all those kinds of things, but as I wrote it down, I said, here's a class in cohomology. And so then we have to formulate, what does it mean for, what do we really mean for this to be pseudo effective? What do we, all of these kinds of things. Okay, so these are all very, very important comments. Okay, so for a coherent sheaf, F on a curve C, maybe so I can write it as the direct sum, so E plus T, where E is a vector bundle and T is torsion. Okay, so let's assume that the rank of F is positive. Okay, so we can define its slope. So the degree divided by the rank. Okay. So so a vector bundle E is semi-stable if the slope of some vector bundles is always less than or equal to slope of E. So maybe I should just state that, recall the existence and uniqueness theorem. Cool. Okay, so suppose E is a vector bundle on C. Okay, so then E admits unique filtration. Where each of these successive quotients is semi-stable. And then slopes of the subquotients strictly decreasing in all of the sense. Okay, and so I mean, so there's many reasons, of course, why the existence of harder and Narasimhan filtrations is significant. So I mean, one, it gives a measure of how E fails to be semi-stable, in the sense that this is what I mean. This is in some sense the point of the filtration, but also the sort of the numbers that appear. This is what I want to place some emphasis on. in what follows. So I'm wanting to denote, so mu I is the slope of this of the successive subquotient. Okay, and then Ri is the rank of the successive subquotient. Okay. Okay, so now I'm going to say a little bit more about the Harder-Narasimhan filtration result. That I alluded to in the introduction. So as I said, so this is one of the steps in proving these semi-positivity results that I described for you very briefly. So just consider the following case, that you have E, a vector bundle on C, okay, C is a curve with genus G. And so look at its Harder-Narasimhan filtration. Okay. So now what I want to do is fix a close point on the curve. And now we can basically look at this filtration along the fiber. Okay, so so the idea is study where certain global sections of E become simple tensors. Certain simple tensors along C. Okay? So study where certain global sections of E become simple tensors along T. Okay, so I have to spell out in more detail what I mean by that. So in more precise terms, so restrict this filtration to T. Okay, so what this gives is a filtration of vector spaces on the fiber. Okay, so now let EI be a basis of ET that is adapted to this filtration. Okay. So a basis of the fiber that's adapted to this filtration, and the point is that this filtration is induced by the Harder-Narasimhan filtration of E. So it's some global filtration that we want to understand is how it behaves sort of about a particular point. And so then we're asking, in some sense, how these sections sort of interplay with the risk of filtration. So that's kind of what I'm trying to capture with the intuition when I make that remark. Okay, so now consider for each positive M, the evaluation map. From the mth tensor power of E. Okay. And what I want, again, working sort of on the fiber, let GMT be the linear subspace of the image of this map that spanned by pure tensors in the I. Okay. So is it clear how the definition of this subspace is trying to capture, in some sense, what I've said here, right? So that's the point, is that we can, and so what we're trying to do again is ask, sort of fiber-wise, how global sections of the tensor power of M, how they accumulate. And the interplay with the Harder-Narasimhan filtration is the fact that we've locally chosen the basis that's sort of induced or compatible with the induced filtration. Okay. So that's the, okay. So then, and what's very interesting is, so as an application of the central limit theorem, the main Harder-Narasimhan result, the article CP is the following, is that asymptotically we get everything. So meaning that E has positive degree, the limit as M goes to infinity, the dimension of the subspace divided by the dimension of the mth tensor power restricted to the fiber, that this is equal to 1.
So in some sense, for M big, this scheme will be globally generated, right?
Well, I mean, that's what you're doing this at a particular fiber, and you're actually saying a little bit more in the sense that you're saying it's right, sort of fiber-wise. One way of thinking about this is that you're globally generated, but by special tensors, and that's actually significant. That's actually significant for the applications in mind, because again, so you should imagine the setting of a family of log Fano varieties, and you want to say something about K-stability or things like that. So you need to say, you need to have some understanding about certain kinds of sections that have some special property, and you want to exploit that information to prove some sort of global generation is morally what's happening sort of in the background. Very concretely here, this is what's happening. And that's the main thing I wanted to explain today, partly because, again, this sort of principle works more generally. Okay, so that's what I want to make a bit progress explaining now. Okay, so first I'm going to just start with a very concrete sort of definition by Harder-Narasimhan data. All I mean is meant a collection of strictly decreasing rational numbers. So these are the subquotient slopes, if you will. And with positive integers. Okay, so these are the subquotient ranks. And so denote this by H and U are. Okay, so this is just vector notation for the slopes. Vector notation for the subquotient ranks. And then finally, we can make the degree vector by multiplying the subquotient slopes by the subquotient ranks. And then we can impose the condition that this Harder-Narasimhan data has positive degree. So the Harder-Narasimhan data has a positive degree when essentially the degree of the bundle in this sense is positive. So that's the, you know, abstracting, right, in the most say obvious sense, the numerical data that appears in the Harder-Narasimhan filtration of a vector bundle in a curve. And so this turns out to be interesting. So this is example, or example one is each vector bundle E on a curve C determines Harder-Narasimhan data. Okay. Okay, and this is positive. Exactly what I mean. The degree of E is positive. Okay. So now I'm going to sort of move into the sort of bubble over here that I wrote at the start of the talk, right? So we have sort of birational classification, we have stability questions, and then we have complexity and distribution of rational points. And so I've talked about more, over here with a bit of birational classification. So now I'm going to talk a little bit more about cryptically, in some sense, about the complexity and distribution of rational points. And the reason, again, is because I'm really only going to be talking about sort of a structure that arrives in the proof of those theorems, and not necessarily about how those theorems are used to prove statements in that sense. And so, again, one of the interesting things that's happening here is just the interplay of techniques across these questions, aside from the fact that there's actual interplay amongst the statements of those amongst the statements of theorems in those areas. So this is sort of the second main example of where this Harder-Narasimhan data arises. And so this is in this context of vector spaces. Okay, so this is, for example, as in the work of Faltings and Wustholz. So by the theory of Faltings and Wustholz, each filtered vector space V determines a Harder and Narasimhan filtration. And it's Harder and Narasimhan beta. Okay. And so I'm going to use the same notation, but I should remind you a little bit about what we actually mean by, say, the slope of a filtered vector space. And one of the things that I had intended on talking a little bit more about, but decided to sort of omit for reasons of time, was to sort of briefly maybe recall some of the main steps in the case of vector bundles on the curve about how you actually prove existence and uniqueness of the Harder and Narasimhan filtration. And the reason is because once you understand how that works, the proof of the existence of the Harder and Narasimhan filtration follows the same sort of strategy. There's sort of one point that I should mention is that, so here, I mean, right, so these numbers that are appearing in the filtration, they can be rational. I mean, more generally, they can be reals, but if they were reals for to sort of produce this Harder and Narasimhan data as they did, there's two rational numbers instead and proceed. So that's sort of what's intended. But let me also mention what the slope is, so that way you'll have a better.
Sorry, but what is the slope here?
Yeah, exactly. So the slope of the filtration So as I said, how do you, so how do you prove this? I mean, you have to do the sort of usual, sort of strategy that you do for the vector bundle and curve case. So for example, there's the usual properties. So I mean, what do I mean by semistability? First of all, right, I'm going to look at subvector spaces, and I'm going to look at the induced filtration, and I'm going to ask the respective inequalities among slopes to behave in the way that you'd expect, and then the inequalities will go the other direction when you look at quotients, things like that. Okay. So that's okay. So that's what's going on. Okay. So okay. So now I want to just consider. Consider positive degree. Filtered vector spaces. Okay, in the sense that this condition is satisfied. And so that's why I mean, one of the reasons, again, why packaging this data in this way is useful, because it allows one to say something about, for example, what do we mean by a degree of such a filtered vector space in this way. Okay, so now by analogy, with the fiber-wise vector bundle story that I just talked about. So it's interesting. To ask how the Harder and Narasimhan filtration of a filtered vector space interacts with the m-fold tensor power of V. Okay, so both of these results, these settings can be they analyzed or considered together in some sense. So in order to spell that out, I'll have to sort of do a little bit, you'll see a little bit more of the technical details now that kind of are under the hood of the result I just mentioned, but also we can just sort of see what's happening more concretely just for the vector space and see how this all fits together. So, okay, so to get a flavor, so fix an integer bigger than or equal to 0. And for m bigger than 0, considering side of the tensor power the m, the following subspace, which I'll say a little bit more, at least maybe at the end, hopefully, if I have time, but it's I'll try to just give the sort of bare amount of descriptions for how you might get some understanding for right now. Okay. Okay, so these are pieces of the Harder-Narasimhan filtration of the filter vector space, and I haven't told you how I selected sort of these sort of which index or which step, and I haven't also told you about what this set SM Z is. Okay, but the point is that this subspace is spanned by certain m-fold tensor products that arise in the Harder-Narasimhan filtration of the filtered vector space. Okay. And so now the point is that so the point now is the central limit theorem implies that asymptotically as m goes to infinity, this actually spans the m-fold tensor power. Okay, so the way to sort of phrase that theorem assume that the degree vector is positive, then limit is infinity. The dimension of this subspace that I briefly described for you, let's say a little bit more. So the ratio of these dimensions equals 1. Okay, so this is the filtered vector space, right? So this is the filtered vector space analog of CP. So maybe so I have about 5 or so minutes. So maybe I should try to give a little bit more details about, again, why is this the right, like what's happening here? Why what's the relation? I mean, how do we see where the central limit is coming from? And why is this the correct sort of subspace? Okay, so let me try to say a brief outline of the proof. Okay, so brief idea of proof. So inside of sort of the mth Cartesian product of L, so you could sort of think about like a Wietig product trick is sort of getting used in the end, and this is partly true. And so what I want to look at is, again, certain couples that have the property that the subquotient slopes are at least okay. And so then this lets me define a suitable ordering. And so then what the ordering lets me do is lets me decompose this set into the following disjoint union. Okay, so what's happening is that this set that appears here is going to be the first sort of collection where I'm not starting to decrease. Okay. Okay, so then the key relation. So the key relation that uses that links with the sort of central limit theorem is the following. Okay, so the sum from 1 to D, the product J from 1 to M. So this is the subquotient rank of the piece of the Harder-Narasimhan filtration that's indexed by this Aij. Because see, I guess maybe the thing that I should also do with this vector space, so it's sum over these Aij's. Okay, so this is from 1 to M, I from 1 to, again, this M, that. And where these are coming from, it's coming from exactly this. Okay, so that's sort of the index notation that's coming from there. Okay, so what's happening here is so that this when you expand, okay, so this becomes sum over A in this index set S Z product R A J R, and then this becomes now products of these probabilities over the sum. Okay, but sort of the punchline, okay, so is in particular this dimension, ratio of dimensions. when everything is sort of comes out in the wash. This is the sum and the product J equals one B A J. A sum M. Okay. Okay, so the point, right, concretely, what this is saying is that now as M gets large for a given Z, that as M gets large, this will actually be equal to 1. And so, yeah, okay, so anyways, okay, so I'm sort of out of time. So I hope I've given sort of enough idea to sketch the flavor of ideas. And again, there's lots of stuff that I haven't talked about at all, but I think this is really interesting. Because it's, yeah, so again, so yeah, okay, so are there any questions or comments? Or?
Let's first think the speaker one. And let's ask some questions.
So what are some applications of this theorem?
You mean of just the sort of
Limit.
the vector space sort of analog of this? Like, well, so I mean, when do you sort of stop asking applications in some sense, right? So I mean, first, just the fact that you get sort of a central limit type theorem for basically arbitrary Harder-Narasimhan data with positive degree, I think it's just of some interest in because it's highlighting the particular technique, the most important idea behind that sort of technique. And then the fact that, you know, there is this basically analog that the same proof will work for this exploring the fiber-wise, you know, whereas the accumulation of these tensors work fiber-wise for a vector bundle, that also just works for this filtered vector space analog is also of some independent interest. And then the fact that, again, these filtered vector space analogs, that they have a Harder-Narasimhan theory, that's of independent interest, for example, in the Faltings and Wustholz theorem. And so saying something about developing that theory further is, of course, of some, you know, interest. So that's not really answering your question, because your question is more, so I've proven basically this theorem. And so now can I use this theorem to say something even more? And so at the moment, I haven't found further applications of these techniques beyond this yet. So, yeah.
In this case, or in the previous theorem of Codogni and so you have this limit equal to 1, but can you say something on the difference between the ratio and 1? So because it's polynomial, right? Expressions.
Well, so your question is how fat, like what's the rate?
How far and yes,
Yeah, exactly.
This difference.
Right, so that's the first, I mean, you would like to be able to say this a little bit more. I mean, I don't have any, but like, so, right.
Are they able in Codogni? They are able to say something. It does depend on the bundle in a certain way.
You would expect it to, and so, but I mean, can you say more about that? I mean, these are all very, you know, that would be a refinement sort of the question. And in fact, as you might notice that when I stated their theorem, I was able to define a subspace that's slightly less technical than the subspace I actually defined here. So there's, right, and again, this is not being like at a single point. So you could imagine, really, this is a very general statement in the sense that we're basically starting with E of positive degree. And so you would expect there to be a stronger hypothesis that you'd be able to say something more refined or not, but I don't.
So in their theorem, you fix a T arbitrary, right?
Yeah.
So it's true for any T. If you go to higher dimension, or not over a curve.
Yeah, so that's
Does T has some influence? I mean,
also, okay, that's a good question. Could you prove an analog for a higher dimensional base?
yes.
And that I don't know. And there's I should mention, they are using a little bit more about the theory of the bundle on a curve than what. So you could say, maybe if I had a higher dimensional base, could I have a Harder-Narasimhan filtration? Something like that, and then
They're using the fact that the Harder-Narasimhan filtration is given by subbundle.
well, they're using, but then they're also using a little bit more than that as well.
Okay.
So you could try to, so that would be, could you prove a theorem like that? That's a good question. And I don't, I don't have the answer to that at the moment. Yeah.
So
Is it
if you change the base to higher dimensional base,
Mhm.
we should define stability. So
That's right.
stability is related to some divisor. We fix ample divisor H, for example, and we define stability.
So, right, so
There
you,
is not a
so
notion.
you fix, so fix your, so I mean, fix your notion of stability for a higher dimensional base. I mean, so I should mention, just so there's no confusion, I mean, the goal of the goal is to say, prove something about families of Fano varieties. And so there you can say, maybe we can make a reduction to the base being a curve. But as a separate question, if we want to say, can we try to, obtain an analog of this kind of result for a vector bundle on a surface or a vector bundle on a threefold or something like that. So then we have to say, well, so how are we going to make the Harder-Narasimhan data, for example? And so, and then after that, can we still say something about fiber-wise surjectivity or something like that? And so that's the
The symmetric power is not simpler to study.
So I haven't used anything about the symmetric power at all. So I mean, so one thing that maybe is, so I should say, so there's some subtleties that arise when you start talking about these Harder-Narasimhan theory for vector spaces. So in some sense, it turns out that the vector bundle theory on a curve is easier. And so how do you, but I mean, there is this theory about, things like you would like to ask about, like tensor products or symmetric powers and things like that. Can you obtain the analogs of what's, the stability statements that you know for curves? And so, as a sort of the question about the tensor product of two vectors, this is, more difficult, but there's some subtleties to prove, sort of directly using only vector space techniques compared to what happens on curve. So, I mean, in that sense, the short answer again is these are fine questions to ask, but what can be said beyond that? It seems innocent maybe, but in the end, they're actually quite subtle questions. Does that answer your question? Or?
I have two small questions.
Sorry.
Yeah. So at the beginning, you mentioned that the goal is to prove the positivity of Shaw-Mumford line bundle, right? So what is the relation between this theorem, for example, and
so this theorem has a related, not directly, but it would take
the theorem of
right. So that I have to go through the sort of a whole roadmap of their plan of the proof. So that's quite a complicated answer. So
okay, but for example, the theorem of Codogni and this theorem implies the positivity of this line bundle in some sense.
I mean, after
The idea, okay.
yeah, that's part of one of the key sort of points. And yeah.
I have two small questions.
Mhm.
So most important setting is like you have Fano fiber over a curve, and is that so? And then you push out you get the actual Mumford line bundle, and you study the positivity of it in the main setting for the.
That's the main purpose of their paper. That's right.
And it's kind of like to study the moduli space of K-stability.
I mean, that's an application of, that's part of what their results are giving is an application. That's right.
Okay, I have the second one is so you give a filtered space and then you define the slope of that filtered space, and the definition looks to me very much like delta invariant. And is it somehow?
All right. So this is okay. So this, so the short answer is yes. I mean, this is partly also this sort of diagram that I was mentioning about how all of this interplay ties in. This is one way of viewing that exactly. And so that's part of why it's interesting to sort of explore these kinds of ideas in tandem.
But it's not related directly to the delta invariant.
Well, okay, so the delta invariant per se, I mean, so I guess the answer I'll say for the delta invariant in particular, I would say sort of is probably to define the delta invariant. We have to say, how are we calculating the delta invariant? Maybe by M basis divided with that. And so, yeah,
So you expect higher dimensional of this theorem?
Possibly. So, okay, so very concrete, like, Jorge wrote a paper about, slope inequalities, start using the Harder-Narasimhan filtration. And so, part of when I suggested that, in my mind, I said, well, how is the Harder-Narasimhan data related to those sort of slope inequalities? And so after, you thought about it, you worked it out, the answer is kind of sort of, but there's a little bit more, sort of subtleties involved in terms of the ranks of the subquotients. Do they directly sort of play a role in that case? But particularly about this kind of a theorem, the answer is maybe. Again, you have to say what kind of, so what are you going to, what's your starting point going to be? Or how are you, you define your stability? Maybe for, say, pure sheaves, look at the Harder-Narasimhan filtration and really capture the fiber-wise behavior in the same way. That could be possible as well. But so yeah.
Okay, are there any other questions from the audience?
I guess maybe whether follow up if I can. So if you just write down the Harder-Narasimhan data and say, what can you say about that? People have just, sort of, so Chen has a monograph that's almost kind of, that's his sort of departure. And starting from that, what can be sort of said? So that's how sort of general these kinds of, so. Yeah.
Okay. Well, it's time to thank the speaker again.